Okay, here in this video I will solve one of the problem which is given in your book, which is find the potential of uniformly charged spherical shell of radius r. Suppose we have this spherical shell and it is radius r, and we have to calculate the potential at point P at this point. So this is the center of this shell. So here we have the y-axis, this is the z-axis, and this is the x-axis. I will consider a small area element whose area is dA on the surface of this spherical shell. So it is on the surface, so the distance from the origin to this surface is r. Now this point P is at a distance z from the origin on this z-axis. So this distance from the origin to this point P is, I call it z. And similarly, the area element which I consider on this surface is at a distance r from this point P. Let's suppose it is at a distance r from this point P. Then the electric potential at point P, a distance r from the surface charge element dA, the potential at point P which is at a distance due to this area element dA which is at a distance r from this point P is given by this relation, which is dV, which is equal to 1 over 4 pi epsilon naught dq over r. This is for this small surface element. Now if we calculate the potential throughout this whole surface, then I will divide it into small area elements. So if I calculate the total potential, I have to calculate the potential of each area elements, and then I will calculate the total by summing all those potential. But this charge distribution is continuous, so the total potential can be obtained by integrating this equation. So if we integrate this side, so we get V, and on this side we get this relation. Now the charges are distributed on the surface, so I will introduce the surface charge density instead of this dq. So the dq is equal to sigma times dA, where sigma represent surface charge density. Where sigma represent surface charge density. It's the surface charge density. Now if I put this value in this equation, we have this relation now. Instead of dq, I put sigma dA. Now according to law of cosine, I will write the law of cosine here. If we look at this triangle, it is like this. This is R, this is Z, and this is this small r. By the addition of vector by head to tail rule, we know that Z, this is the resultant. So here we have the angle theta, which is equal to this vector r times this vector. So I call it r plus r. If I calculate the value of this small r, it will be equal to Z minus r. If I take the dot product of this r with itself, I get Z square plus, next we have r square, and then we have minus 2 Z r. And then we have cos of theta, because it's a vector product, it's a dot product, and the dot product is basically, if we take the dot product of two vectors, we can write it as like this. I will use some extra pages here now. So we can write it as like this. So we have r, which I call it r, the small r, which is z minus r. Then r dot r will be equal to z minus r dot z minus r. So r dot r is basically r square. Okay, and this is equal to, first I will apply the z vector to this one. So z dot z, and then we have z plus, no, minus, sorry, because there is a minus sign, z dot r, and then we have, again I will apply this minus r to this one, so we have r dot z, and then we have minus minus plus, so it is r dot r. So this is equal to z dot z, it's equal to z square, and we have minus z dot r, and then we have minus r dot z or z dot r. I can write in any way because dot product is commutative. So this is this term, plus r dot r is equal to r square. So we have z square plus r square, I will keep it first, minus 2 times z dot r. So if I open the dot product, it will become equal to z square plus r square minus 2 z r cos of theta, because a dot b is equal to ab cosine of theta. So here I will apply this one. So r square, this is called cosine law. So from this we get r is equal to z square plus r square minus 2z r cos of theta. This is called cosine law. So here according to cosine law, r square is equal to r square plus z square minus 2rz cos of theta. Now next, also in spherical polar coordinate system, this area element dA, which is given by this r square sine theta d theta d phi, this I call equation 3. Now using equation 2 and 3 and equation 1, this equation 2 and 3 and equation 1, we have the value of potential, which is sigma divided by 4 pi epsilon naught, and then we have this term if we put this value here. Now next, I will keep this r square outside of the integral because this is a constant quantity. So we have sigma r square or 4 pi epsilon naught. We have sigma r square or 4 pi epsilon naught. Now we have, this is double integral because we have two quantities now. One is d theta and one is d phi. So I will write d phi separate to this d theta. So if I apply integral to this d phi, then its limits are from 0 to 2 pi. So here we have 0 to 2 pi d pi, and the limits of theta varies from 0 to pi in spherical polar coordinate system. So this is that term. So I just write these two in separate way. So from this integral we get 2 pi. So this is 2 pi del r square or 4 pi epsilon naught, and this integral I write like written above. Now here we put this supposition. I suppose that r square plus z square minus 2rz cos theta is equal to x. Then if I differentiate, if I take the differential of both sides, d of this times d of this, so here we have dx. Now these are all constant, r, z are all constant. So the differential of these two things are 0. So we have minus 2rz cos theta. But if these are also constant, if I take the differential of this, we get minus sine theta. So one minus is from the differential, one minus is here. So it's already become plus. So it's 2rz, and cos theta will become sine theta, and then again d theta is equal to dx. A sine theta d theta is equal to dx or 2rz. If we put this supposition in the above equation, we have this relation now. Now here again these two r z are constant, so we can keep it outside of integral. We have this integral now. If we solve this integral, we finally get this results. So again I put the supposition here because we consider x is equal to this one. So here I put the value of x here. If we apply the limit, we get this relation. Now here we have this positive root, because r plus z whole square will always give us a positive value, and similarly r minus z whole square will always give us a positive value. So we can carefully take the positive root. Why? Now if point P lies outside the sphere, if this point P lies outside of the sphere, is already outside of the sphere, then z will be greater than r. Then this z, distance from this origin of the sphere to this point P, it's always greater than the radius of the sphere. The radius of the sphere is up to this point. So, and the z is outside of the sphere, so z will always be greater than r. Z always be greater than r. Then this r minus z will be equal to z minus r, because z is greater than r. So this is positive root, so this will be positive, this value will be positive, and it is positive only if we subtract r from z. So this r minus z whole square, it's basically, if we bring this outside of this square root, it's r minus z, but r minus z is negative because r is smaller than z, and the root are positive, so we just replace this z minus r with each other, z and r with each other. So this is now positive. Now, and for point which lies inside the sphere, now if I consider the point somewhere inside this sphere, like somewhere here, then what will happen? Z will always be less than r. So this will, r minus z whole square will be equal to, into square root will be equal to r minus z. So this equation can be written for two things now. One is this v is equal to, here this v, which is equal to sigma r over 2 epsilon naught z times r plus z, we get square whole square root, we get r plus z, minus r minus z, we get z minus r if the point is outside of the sphere. So we have this plus z cancel with this minus z, so here we have only 2r. So if we put the value of 2r here, the final result is given here. This is the potential when the point of measuring of potential lies outside of the sphere. Now we know that total charge on the sphere is equal to surface charge density times the total area, and area is basically 4 pi r square of the sphere. So here total charge will be 4 pi r square sigma, or sigma is equal to charge over 4 pi r square. Putting this value above in this equation, we have the value of potential, which is 1 over 4 pi epsilon naught q over z. This is for point lies outside of the sphere. Now for point lies inside of the sphere, we have this relation now, r minus z. So here r cancel with this minus r, so here we left only with z square, 2z, sorry, it's 2z. So z cancel with z, 2 cancel with 2, so here we left with sigma r over epsilon naught. This is for point lies inside the sphere. Now if we put the value of sigma here in this relation, which already we calculated here, then this will become this one. This is the potential for point lies inside of the sphere. So this is the end of the problem. Thank you.